Right, so welcome back to Dr. Carp Society Mission. Alright, so we found the formula for magnetic energy. We said it's equal to half mv squared. When you move it from here to another point, the velocity v. Because your initial velocity is 0, and you got v. Okay, then we derive that. Now let's look at here. Let's assume this is the flow, and then this is a load, mass n. Now we lift this one up to a height given by height h. Okay, now as we lift it up, okay, we are doing work. Now we define work. Work done is equal to force times distance. We have already defined force to be proportional to your mass times acceleration, which we said force is equal to kma, which is the constant of proportionality. Of course, by definition, because this is 1, k becomes, f is 1, k becomes 1. Therefore, f is equal to ma. We have defined that already. So let's use this same formula to derive something for this. If we lift this body to this height through this h, what will be the work done? So work done is equal to force times distance, which means our force. What is the force? The force in action, the force which is moving the body through this height. The height becomes the distance. So the force is going to be the mass of the body times acceleration. Acceleration is what? And in this case, we are moving in terms of, we are moving against gravity. So in actual sense, should have been times negative g. But we will not look at the negativity, we will not look at the sign, because we are looking at work done, which is a scalar quantity. So our mass times our gravity times the distance that we are moving it through, which is what? H. Will mean, of course, that will mean the work done or the energy that will be contained in this system. This work done is equal to, by the time we move this one to this height, the energy that this has is this, because that was the work done that was used to move it to this. Energy can neither be destroyed or created. So that work done will be equal to the potential energy at that point. Okay, and this becomes, so this is the work done. This becomes your P. P becomes what? Mass times gravity times height. This is the formula I wanted us to look at. Good. So we move on. We look at another equation where we say, let's say we have this mass, and then there's an explosion. This mass n moves here, and this mass n moves there. Okay? Now from the law of conservation of linear momentum, if this is what happens, this is an explosion. Before the occurrence of explosion, let's denote momentum. Momentum before is equal to momentum after collision. Momentum before, because this one was stagnant, it wasn't moving. Momentum before was 0. Okay? And then momentum after will be m1, so capital M times its velocity v. Okay? Plus small m times its velocity v. Of course, we will notice that because this one is moving this way and this one is moving, you have to choose a direction. So let's say this direction, let's assume this direction is our positive, those going this direction is our positive sign. Then in that case, m is plus mv, and then capital M will become what? Negative v. From this, we can say that if we bring this one here, it becomes capital M v is equal to small m times 8v small v. Let's make this small v, because it will move with a certain velocity. right? So this will be for an explosion. Now let's look at something. Let's work this out and see how the energy will be distributed between the two masses. Okay, we know kinetic energy, they will be moving, so that will be a form of energy. So we have mv squared. So the kinetic energy of this mass will be half capital M v squared. That's the big mass. Now the small mass we have mv squared. That's the small mass. Alright. Now we know that let momentum, this is equal to this. Let that momentum be equal to P. Let's make it P. This is equal to P. Now, if this is equal to P, we have mv here. We have this here. So we can say that, let me claim this part of the, let's go up so that you see where we are now. So let me write it again. We are saying Ke is equal to half M, capital M, V squared is equal to, let's do that, and then Ke of 2 is equal to half mv squared. Now we are saying that mv is equal to m capital V is equal to m small v. Let's let, this is the momentum of the big body, this is the momentum of the small body. Let that be P. Now let's see what we can do. From here, Ke, kinetic energy of the big mass, is half capital M squared. This is the same as saying half mv v. For this one, it's going to be Ke is equal to half mv v. Now I'm splitting them because so that we get an expression like this, like what we have here, and put place there. In place of that one, we put the momentum there. Let the momentum be P. So you see that this will become half P V. P capital V. Okay? Then this is going to give us what? Half P small v. Okay, right. So we can say that if you look at, if you divide the two equations, then the velocities will be inversely proportional to each other. That is one thing that we can notice from here. Yeah, so you see that if you divide them, then the Ke over Ke, that's the K, this one will be 1, that's the 2, 1 over 2, half P capital V over half P small v. This is going to cancel, and that's going to be capital V over small v. So this, for that, that's equation 1, that's it, and that's equation 2. Alright, so in terms of kinetic energy, let's see what happens. We divide that, that's the P is for this momentum, we have already found it to be the same as that. So if you substitute, this for the bigger mass, let's say that is 1, this for the smaller mass. That is here. So we can even make it 2 so that we have this. And that is what you're going to have. So you're going to have a ratio between that and this. Okay, so that's in terms of kinetic energy, that is how you are going, that's the ratio that you are going to have. Alright, so this ratio is something that is you can use to work things out depending on. So it's that the masses, the kinetic energies are proportional to the velocities. Now let's look at a relationship where we want to eliminate V. Now if we want to eliminate V, let's look at that. Then we'll try to write the same thing. Let's see, this, let's say M V, to make it squared, then it means it's M that we have added here. Because this is, let's say if we multiply here, let's say we multiply here, the top by M, and then that one by M. So that if you multiply the top by M and that one by M, we will come back to have what? Half mv squared after m over n. This is what I mean. Now this is similarly, if we multiply here by small m, we're going to have half mv squared over small m. Of course, we want to eliminate m and we want to eliminate v. That is why we are expressing it like this. So this will come down as what? Half v squared over n, and this is going to give us half p squared over small m. Now this is the kinetic energy, this is the kinetic energy. Now let's divide, let's say kinetic energy 1, kinetic energy 2. Let's divide this equation by this equation. Then we're going to, if you do that, we're going to have this over ke2 and this over half p squared over n. What do we get? This is going to give us, this will cancel that. Of course, this is going to become p squared over p small p squared, and then this m is going to go on top over m. You see this cancels that, and that is going to give us with the small m capital M. Now what do you notice for this equation? What do you notice? You see that the kinetic energy is inversely proportional to its mass. So the smaller your mass, the greater your kinetic energy. The kinetic energy, or the energy, which is also the same as the energy, is inversely proportional to the kinetic energy. Okay, right. So this is what we wanted to prove. That when there's an expression, the smaller mass will have a greater kinetic energy, and then the bigger mass will have a lower kinetic energy, because this K1 is inversely proportional to its mass. Its mass is down. K2 is inversely proportional to its mass is up. If they were the same, they would say they are proportional, directly proportional. Right, that is what we want to prove. Now let's move on. So the real gas equation is like this. Now P plus our A over V squared, then V minus P is equal to this. This is the real gas equation. The real gas equation. We have the ideal gas equation there. The ideal gas equation, PV is equal to N RT. This is the ideal gas equation. Now you see that here we have added something to P, and here we have subtracted something from P, because we assume that in the ideal situation we said the particles of the gas, we can say that they don't have mass, no mass, okay, and neither they don't have volume, they don't have volume, negligible, okay, right, and then there's no force of attraction, no force of attraction, or no forces of attraction or distance between them, so force is also out, okay. Now, in accounting for that, this portion has been added to P to correct for, this is a real gas situation, so this portion has been added to P to correct for the change in pressure, because this is not a real situation. Now, because at this point, when it comes to volume, when we are correcting, we then see that the gases now occupy volume, so we have to subtract the factor from V, and that is why we have the subtraction of V there. Then we are out. This, we'll come to this later when we get to the kinetics of the real gas, and to derive the real gas equation using kinetics. We'll come to that one. Alright, so this is just a brief thing to talk about. We'll use this formula. So this is the Van der Waals equation. Now we move on. We can use what we call the kind of a linear method or proportionality method to derive some formulas. For instance, if we have this as our pendulum, this is the length, this is the mass, and then of course there's gravity acting on it. Okay, we can say that the period t has the time taken to go. Let's say if you move from here and come back, the time taken to make a complete circle movement or revolution is t. That t will be proportional to the length, proportional to the mass, and proportional to gravity. Okay. Now, if we assume these proportionalities, then we don't know whether this one is to the power 1 or negative also. So we can just, let's say, this be x, this be y, and this be z. Okay? So if we do it this way, then we can use this kind of equation to derive an expression for t. So let's see how that will be done. So let's see. Right, so this will, of course, if you remove it to be k, l, x, m, y, g, z. Right, now from here, we must say that the period, this period, which is time, actually in seconds, this is in seconds. Okay, this is the length. This will be meters. This is the gram, so kg, and this is acceleration due to gravity. Acceleration due to gravity is what? Per meter square. Okay, per meters square. Mass per meter square. Okay. Alright, so let's look at what happens in this case. We have the three fundamental units. Fundamental unit for physics. Okay, we have length, we have mass, okay, length, mass, of course, and then we have what? Time, our time there. Okay, so that's what we are trying to use these fundamental units to get the equation. Right. So in that case, our t, our time here, whatever is here must be equal, is in seconds. This is in seconds. Okay. So anything here must be equated to its mass here. Alright. So that the length will become x. Let's say mass becomes y. And association due to gravity, which is going to be what? It's going to be, we must express it in this one. It's going to be mass, which is what? M over time, which is t. T what? 2 here. All this, we said this should be z, so z. So our time here is also in seconds, okay? This is also in seconds. You can have it there. Now, if you look at it from this direction, length, there's no length here, so it means x must be equal to 0. X must be equated to 0 here, because we don't have any length here. Or let me put it this way. Right, so let's see how the equation will go. So this is our, let's make it, this is meters, okay? It's meters, so that you don't make that out. That is what it's called. So I think here meters, it's going to be L, okay? That's going to be L. So that's L here, right? And this is Z, okay? Our time here is here, 1, T. Now let's see what happens. Now this length that's going to be proportional to L. Let's bring this one out. Times L to the power 1. M to the power y 1 over t squared. This can be rewritten as what? L, this plus this is going to what? X plus 1, this because it's times, plus times my times what? T negative 2. Of course, we shouldn't forget this z affected it, so this is going to be z. because this is affected, it's going to be C, right? And then we have our M here. The T is going to be affected by Z here. Alright. So from here, we're going to have this L has come out to be S as this. And there's no L here, so S plus Z is equal to 0. Y is equal to 0. That is the mass is equal to the M, Y is going 0. T here is 1, so we're going to have 1, negative 2, Z. Alright, so from here, let's see. So from here, this is equation 1, equation 2, equation 3. Now you will see that this is the same as saying from here, our negative 2 that we have here. Of course, that is what we have. If we substitute that one, let's make Z the subject and put it there, C. So this is going to be divided here by negative 2, so that Z is equal to this. Now, if we want to find the answer, because we have found Z to equal to half, negative half, we can put negative half there. X plus negative half is equal to 0, so that X is equal to what? Half. Y is equal to 0. We have already found. So from here, this is what we have used to get our answers. Well, now we can put this back into the equation and see. We can say that from here, we said the initial equation T is proportional to T is equal to this. K L X M Y Z G Z. Now let's put the values that we got there. This will be equal to K. L is not X is what? What is X? X is what? Half. So L is half. And Y is what? 0. Z is what? Negative half. Now let's write this properly. So T will be equal to what? Okay. Now this is M number raised to the power 0 is 1. So this is going to be M is going to be 1. L half is the same as square root of L. And this J, so negative J raised to the power negative half is the same as what? Square root of J down. Okay? Now, and then this is going to give us what? T is equal to K or square root of what? L over G. This is the equation we want. T is equal to K square root of what? L over G. This is what we have proved. So that the time period or the time or the period, the time taken to go around or to make 1, 2, and 4 is equal to T is equal to K. K is a constant of proportionality. Of course, this will be found to be 2 pi later from my equation. T is equal to this. This we can, so we can use this calculation, this method, to derive a lot of equations. So this is one way to derive it. Right. Now, let's look at it. Let's go to circular motion, and then simple harmonic motion. Look at that. Now, let's look at this. This is a circle. This is what you have here. Let's assume this is the radius. Now, initially, this is for the body to move in this is moving this way. The body to move in a circle, the initial attempt is to go tangential. This is the tangential. Okay, to go tangential. And then, of course, for the body to end up going in a circle, there should be some sort of friction here. So we have friction here. Plus, if the road is banked, it means maybe if the road is like that, and there is the car. Okay. Moving. If the road is banked, then the body of the car will also make some contribution. We call that reaction, the normal reaction. Okay. So the normal reaction. Now these two will also try to move the body. Will try to move the body towards the center. Okay, and that part we call centripetal. Okay, now the resultant force will be this, and that is the net, F net. Okay, so that you see that at every point, when it moves from there to this point, the same thing will happen. So that at every point, we have a force that is trying to go tangential, one that is trying to move it towards the center, so that the body ends up going in between. But if you have a body like this, and somebody is pulling it that way, you are pulling it that way, it will end up going in between. That will be the resultant for the net. Right? That is exactly what is happening. So for you to move in a circle, your initial attempt is to go as if you want to go straight. You are trying to go straight. Then the friction, you use the friction of the road as well as the mass of your car, if it is the road is banked a little, to contribute to the force that should let you go towards the center. Okay? So by doing so, you have two forces. One is trying to push you towards the center, one is trying to go this way, so that you end up, your next movement will be like you are going in between. And that is what is going to be done at every point in time in small numbers throughout the circle, so that if you end up going around the circle. Now, if you have this principle in mind, so there is the centripetal part, there is the tangential part, and there is the force, the net force type. Okay? All these forces will have their accelerations, they will have their velocities, they will have their what again? So in these two terms, they will have the accelerations, they will have their velocities. Okay, so we can have the tangential force, okay, having its expected acceleration that should go with it, having it expected, of course, once there's acceleration, it means velocity is changing. And then the centripetal one is also going to have its acceleration, it's going to have its velocity, and so on. Then the net, of course, will be the resultant of the two, will have that. So you have to actually pay attention to the question and then do the calculation as such. Now, the one that we are interested in now, having understood this principle, okay, so when it comes into the same thing, if the body is here, we have a tangential, this is the tangential, Ft, and then there's a body trying to move it towards the center, this is the centripetal, F centi, and then we have the resultant, F net. Okay, so the same thing is going to happen around the circle, so that the body ends up moving in the circle. Now, let's look at this. So you have at the back of your mind, these things that we talk about, this is linear, so it's going to give us a linear acceleration, of course. Now this is also being directed towards the center, that to have its component as linear, and this, of course, is the resultant, so to have its component as linear. So we can have linear acceleration. We'll come to another one we call angular acceleration. So now we are focusing on linear acceleration and seeing how we can get equations for it. Now, we see that acceleration is given by the change in velocity. From the first motions equation, change in velocity over what? Time. Of course, it can also be changed in time. If you are starting from 0, then t becomes t. Right. Change in velocity over change in time. That is acceleration. Good. Now, if the body is moving in a circle and it is moving with a constant, linear velocity. Okay, constant velocity. That's the linear in the linear sense. Okay, that's the velocity. It is moving with a constant velocity around the circle. Now, if velocity is constant, then v final minus v initial, or u is equal to v. So that this means a is equal to v minus u over t. This, we are saying v is equal to u, so this will be 0, isn't it? In terms of magnitude, that is in terms of size. That means acceleration should be 0 when you are moving around the circle with a constant velocity. How is that possible? Okay. It's possible because we are looking at it as magnitude only. But don't forget, velocity and acceleration are vector quantities. Okay, they are vector quantities. So if magnitude is not changing, what happens to direction? Look at direction. At every point, it's changing direction. It's changing direction, and therefore we will not say that a body moving with a constant velocity in a circular path does not have. We will not say so that it does not have acceleration. It has acceleration because the direction is changing. Although the magnitude is not changing, the direction is changing. Right. So that's the principle I want us to get now, or what I want us to take home now. That if a body is moving around a circle, so far as its direction is changing, irrespective of the velocity variation, there is always an acceleration. So there's an acceleration because there's a constant, or there's change in velocity at every point along the path, the circular path. Right. So having had that in mind, now let's move on. Let's look at the next step. Let's try and then derive an equation for linear acceleration. Okay, the linear acceleration is, of course, that is the acceleration of the body as it's moving through this. Okay, but don't forget, let me just make this point too. This F net, the F net, or the resultant F, tends to be more closer to the centripetal force. So it's more or less the same as the centripetal force, or it's approximately closer to centripetal force, in the sense that the body does not move out of the circular path. It's always being directed towards the center, so that it is more proportional to the centripetal force, or the force towards the center. So that can help you to do the calculations for centripetal force and then derive an equation for linear acceleration. Now let's take this one. This is our path. This is what we have for a very small angle. Let me put it this way. This is it. Okay, this is theta. At this point, we have another angle. Now let's see. This angle is here. Let me use the circle so that you get the picture very well. This is the circular path that we're talking about. This is the center. This is it. This is the next motion. From here, this is the direction. And this is another target. We want to find the change. We want to find, so this is the initial velocity. It will have F tangent. It will have its velocity. It will have its